Hello, 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 we, she, hello, Andrew, hello, Vivian, hello, so fast. All right, awesome. Good afternoon, Lakshmi. Hello and good afternoon, we, she. Good afternoon, Vivian. Good afternoon, Alyssa. Good afternoon, Andrew. Oh, and good afternoon from everyone back to Andrew. It's so community spirited of him. Good afternoon, Jaylin. Hola, ¿qué tal, Nicholas? Hello, Charlie. Hello, Stephanie. Good afternoon, Catherine. Hello, Michaela. Good afternoon, Catherine with a Y. Sorry, let me back up. Good afternoon, Catherine with an an I. Hello, Michaela. Good afternoon, Catherine with a Y. Good afternoon, Brenda with a Q. Hello and good day, Josephine with the correct pronunciation. Good afternoon, Warda. Good afternoon. You're very sorry. I can't. Good afternoon, Gabriella. I'm not laughing at Gabriella. I'm laughing at the compliment. That's very kind. I can't even read it out loud because I'm blushing. No, you guys make lab fun crazy. I'm still like verklempt from the lab. Good afternoon, Jayla. No, yeah, I'm laughing. It's really bad that Gabriella even brought up the lab because I had to do like spiritual mental exercises before starting this class. It's actually why I'm like 2 minutes late. I had to like do exercises to try to convince myself to not talk about the lab at all with you guys and just get straight to it, because if I let myself go down that road, I'm never going to get back to the actual physics. No, I really, wait, who else did I not say hello to? I'm sorry. Wait, let me just look. Yes, hello, Luigi. Hello, Andrew. Hello, Vivian. Hello, Gabriella. Yes, okay, I think that's hello, weird extra space that represents me because of my board, which is weird. I think that's everybody. Okay. Oh, did I say Alyssa? Hello, Alyssa. I'm not sure if I. Oh, hello. Hello, Celine. I'm never going to be able to pronounce her name again. Okay. Yes. No. Hello. 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 Okay. Hello, Celine. Spices Lab up a bit. Spices Lab. I think I understand that, Nicholas. Spices Lab. No. All right. Wait. So okay, we have. Okay, I'm going to turn the board to remind me to really get to it. If I'm not careful, I'm never going to get to it today, and I'm going to blame y'all. Okay, first of all, I still owe you tons of stuff. Let me just get out of that way. Father confessor, like I owe you stuff. For the overwhelming most part, none of you owes me anything, certainly not anything big. I owe you, I apologize. Again, the only one I'm aware of it. I'm just saying, like, it's not lost. I have a bunch of game turns to get back to you, and I certainly have the homework ones to get back to you. The only compensation is we're still on homework one, so there's more people coming. So we're doing fine in the curriculum, but you're not going to worry. I'm not going to worry about you giving me any kind of homework to or anything until I catch up to you. So, but I do apologize, and I am aware, and it's not lost. And I think a lot of you did get, I think you got the most recent game turn back today, but don't, which is good because I'm just trying to make progress, but don't, if you got a game turn back today, like the most recent one, but you're thinking, wait, I didn't get back number 5 or something, that's probably true. It doesn't mean I know that. Like I just went a little bit out of order. Don't think that I don't know that or something. Okay. Please disregard what, Lord? Okay, I guess I'm supposed to disregard. Okay, but I don't know, can I just, okay. The Lord part caught, okay, I'm gonna disregard. Sorry, it's one instruction I'm very bad at following, actually. Okay. I want to get to physics. I want to kind of, I'm sure many of you are dying to finish homework one, even just for linearity's sake. And I'd like to too. I want to get back to homework one today. I want to, we spent all this time like talking about the backgrounds of question 4 and 5. We're finally done with all that background. And again, for some of you, maybe you've even seen that background before many times. So at least I want to move on to question 6, 7, and 8. Now 9, 9 is another big discussion. I got to tell you right now, we're not finishing question 9 today, for good or for bad. 9 is what really labs number 1 and number 2 are really about. I mean, and 9 is really the new material, the material that is new to all of us. It will take us time to go through 9. I just want to remind you all again, that is not because we're falling behind or COVID or something like that. Like, it is always the case in this class that homework 1 is like the template, you know, or the I don't know what, the framing device for everything to come. So it's always the case that we spend a long time unpacking all the elements of homework 1 so that we can go into the rest. And for some people, that's very good. But I just want you to know that's just the way it is in this curriculum. For good or for bad. It's not because you're messing up or I'm messing up or something like that. Okay, so we're going to go back. So the first equation on this page on the screen right now, the first equation is in my mind, and stop me if I'm wrong, it's in my mind, it's the summary of it's the conclusion of all of the discussion of work, kinetic energy, conservative forces, closed path integrals, and potential energy. Like that statement, and this is why it took us so long to get there. Like, let's just be clear again, maybe even write this down. Like the first statement on the page, on the screen right now, KE plus PE at any one given place is the same as KE plus PE at any other given place in a conservative. So that is my statement of conservation of energy as it plays out in physics. Like that statement on the top is what we mean when we say conservation of energy in physics. And what we really mean, and again, I think it is the finding, the takeaway, the conclusion from all of this stuff that we've been talking about for like 2 weeks, right? Having established work as the path integral of force, having established that the path integral of force known as work leads to a transfer of something that we hereby from now on call kinetic energy. Having established that work transfers kinetic energy, having then established that there are certain forces known as conservative forces, which around a closed loop around a closed path, around any closed path over any round trip from there to back here again, certain forces known as conservative forces will do a net amount of 0 work around any closed path. Such conservative forces include the gravitational force and the elastic spring force, right? Since there are some forces known as conservative, which will do 0 work over any closed path, that is, they'll undo anything they did or they'll do anything they undid, then we back up and say, okay, for any system at all, any mass, large or small, any system on which no non-conservative forces are doing work, right? Again, this is a summary, but this is what we're saying. From here on in, we're saying, if you have a system that has a bunch of forces doing work on it, as long as you know for a fact that all those forces doing work on it are conservative forces, then you know for a fact that any round trip that system undergoes, any round trip from some place to some other place back to the original place, you know for a fact that system will ultimately not change its total amount of energy at all, its total amount of kinetic energy at all, its total amount of 1/f(mv) squared at all. You can then say, and from here on in we do say, okay, then we have this convenience, this computational advantage, this construct in our mind where we say, okay, great. We already know that as long as the system returns to its original place, no work will be done. It won't change its energy. Therefore, the only changes in its energy that ever occur are when it moves from one place to another. So we say from here on in that any system that is at any place other than its equilibrium place we say that any system that's at any place other than its equilibrium place, we say, you know what, any energy that it's lost, any kinetic energy that it's lost because we did work on it to get it to this non-equilibrium place, we say we're gonna bank that loss of energy in our minds and call it stored up potential energy. Because we know if the thing ever returns to its equilibrium, it'll get it all back. So we're going to call any energy that it has, we're going to say that anywhere it is at all, whatever it's lacking in kinetic, we're going to call stored up potential energy. And then we're going to say, therefore, from here on, and again, for anybody who just tuned in or whatever, I'm just summarizing, trying to summarize or translate the first statement on the page right here on the screen. I'm saying from now on, then, any conservative system, we can compare any two locations, any two places. And I literally mean, I'm trying to jump in places, like points in space, as opposed to, say, points in time. Any 2 points in space, call them x1 and x2, we're going to say the total amount of kinetic plus potential that it has at one place must be equal to the total amount of kinetic plus potential that it has at any other place. The total amount, and that's what we mean by conservation of energy. Your total amount of all your kinetic and all your potential is called from here on in your total mechanical energy. And now I'm saying that I'm trying to sum all this up. I'm also, in my mind, I'm sort of secretly fantasizing that maybe some of you are writing some of these details. I'm also thinking that I'm expanding the details of this equation as I say it. So I'm saying the left-hand side is total mechanical energy. The right-hand side is total mechanical energy. I'm also saying then your total amount of KE plus PE is what's a constant. I'm trying to emphasize that it's a constant from place to place. Energy is a model or a commodity that we track from place to place. It allows us to make one-to-one correspondences and predictions between place and speed. Again, remember, that's the whole breakthrough of this whole thing, honestly. The reason ever to care about energy is if you have a situation where someone says, I name the spot, I want to know the speed. Or if they say, I name the speed and I want to know the spot. That's something we really couldn't do elegantly without energy, because until energy, all of our physics is all based in time. We now have a way of basing things in space. And it all comes from that original construct of force acting through space, integrated and known as work. So the last expansion I want to just make here, or clarification or whatever, is if from now on we're saying total mechanical energy is conserved when it is, right? It's conserved when it is. It's conserved in conservative systems. It's conserved in systems on which no non-conservative forces are doing work, right? But when it is conserved, that term KE on the left, this is where you might want to jot this down. I'm afraid I'm going to like corrupt the screen if I try. But KE, for all intents and purposes for us for the rest of this course, KE is always 1/2 mv squared, for sure. PE, I want to emphasize again, is not the straight up memorizer. PE technically is the path. I mean, this PE is whatever it is. PE is the amount of work done by the conservative force to restore system to equilibrium. I mean, technically, and you have this in your notes, this is where it would get messy if I wrote this down again right now, but PE differs from situation to situation. Like the PE for springs is 1/2 kx squared. The PE for gravity is mgh. If you had a vertical spring that was being subject both to elasticity and gravitation, you'd literally have to include both 1/2 kx squared and mgh in this PE term. PE means all the potential energy you have due to all the conservative forces doing work on you. How do you get each equation for each potential energy function? What you literally do is do the integral, the path integral of the conservative force with respect to displacement. Like PE is the integral from any arbitrary x back to 0 of f dx. Okay, so it has to be calculated. It's not a memorizer, but that's a summary. That's a summary of, I think, everything we said for the last 2 weeks. Work as an integral, kinetic energy as the a transfer of kinetic energy as the result of work, conservative forces being forces that do no work over a closed path, PE being the work done by a conservative force to return to equilibrium, KE plus PE being a constant from space to space for any conservative system. That's what that top equation means. Okay, I'm going to pause for a second. I'm going to, but there's things in the chat. Sorry. Hold on, let me look in the chat. I know I've been bad with, hold on, I'm just going to, all right, there's things in the chat. So, sorry. Okay. Pardon me for a minute. Okay, I'm just responding to the chat. Hold on a second. Okay. Oh, all right. The second, all right, so we're going to go back to physics. The second equation on the board is like what we're going to, the second equation on the board, we have not said yet, just if you're tracking, like the first equation I now feel that we're responsible for. I'm going to practice it one last time right now and just banging out question 5. Because I don't know that we technically did that in this room. I don't think we did. So I'm going to quickly apply the first equation to question 5 and get an answer. Just again, I think I might have written it and might have had you copy it, but you check to see if what I read out for question 5, like seems consistent to you with everything I just said. Then the second equation on the screen is what we're trying to get to. You haven't seen it yet. I mean, not in this class. We're trying to get to that with question 9, and we may or may not by the end of this class. Okay. All right, so I'm going to turn I do want to say again, really, just for whatever it's worth, as a human being, I'm fighting every instinct, really, to stay on the curriculum and not talk about yesterday's lab with you. I mean, in a fun way, because really, I did promise I wasn't going to be there yesterday. I really actually had somewhere else that I really actually was supposed to be. I really did cancel that because I could not resist. I mean, obviously, we had a problem. We had someone needed to cover it, but I couldn't resist because it was too much fun to be with you guys last week. And it really is soothing my soul to now feel like I'm getting to know you people. And it really it makes me want to be back in the classroom all the time with all of you. It, like, really, just so you know, I had a lot of fun with you, and I'm not faking that. And it's not me, it's you. I mean, I've been covering some other classes too. It's not quite the same. So I just really want to say I appreciate the spirit in this room and the fact that you're all continuing to hold on with any degree of enthusiasm, let alone the good spirits that you are. Like, really, just know I'm fighting the instinct to spend this entire 75 minutes just like lavishing sentiment upon you. You're probably adding 25 years to my life and my career, really. And I think I think you're on top of the material. Like, I actually do think you got what happened last week and yesterday, and I think you're right where you need to be for whatever it's worth. And I see that everybody's working. So thank you. Again, I'm looking away. The light is just too bright for me to handle, for reals, yo. Okay, so we're going to go back to question 5 now. I hope you do know, though, now that I feel like I'm getting to know you better and like I'm knowing some of the names better than the faces, please use whatever experience we're getting to have in the lab together. And I do hope we have it again. I hope, like, whatever, I hope another thing occurs. Please do, if nothing else, take that lab opportunity to like interrupt me more here and take more liberties here. I mean, I hope you're seeing really the more, maybe not just to get off the topic, but like the more you guys inject yourselves into this dynamic, it really is the better for all of us. Honestly, like, I mean, I hope you see that. So please do. But okay. For example, I'm about to do question 5. You could totally say, yeah, Ram, you did question 5 4 weeks ago and we're sick of it, or the reverse. You could say we never even did question 3 or something. Yeah. Okay, that's funny. That's funny. Okay, you've clearly gotten my message. All right, fair enough. You know, if you said that twice, I would believe you too. I mean, about question one, but okay. Oh my God. Oh my God. Um, okay. What did I do? Question. That is funny. Okay. So question 5. Okay. So, okay, yeah, I was just ignoring the chat. So okay, so I think I'm doing question 5. I honestly don't. I think I might have written this for you once. I think, and again, this time I'm going to write it sort of fast, but you tell me with whether it jives with. Oh yeah, I guess I did actually do this one, but it's okay. Yeah, I guess I did, but. Whoop. Okay, so this is just everything I'm writing right now is an application of the first page. I mean, the first screen to this problem. So I'm saying in general, you know, total kinetic energy plus total potential energy over here equals total kinetic energy plus total potential energy over there. You have no gas. I have. Okay, I have. Okay, I appreciate it. All right, I'll try to do this quickly. I guess I have done this. Yeah. Okay. But total energy over here equals total energy over there. Total energy means all kinetic plus all potential. Kinetic always is 1/2 mv squared. Potential in this case is 1/2 kx squared. Again, if I'm trying to emphasize anything now, is to remind you, if you're wondering ever, like, where did I get potential energy is 1/2 kx squared? I got it because that's the work done by a spring to go from spot X to 0. Like when we originally did that integral, even in other words, by the way, notice that we figured out that integral and got 1/2 kx squared before we even knew in this class about the concept of potential energy. 1/2 kx squared was just the work being done by the spring. So technically we could solve all these problems just knowing about work and kinetic energy. We've already done the integrals that are necessary. The whole potential energy thing is just a throwback to work in reference to conservative forces. So, I mean, so it's just a faster way to do the same thing, to use the same integral results. But okay, so we have this. Yeah, okay, so I already did this. So yeah, I totally did do this. You're right. I'm sorry. Okay, but so right. All right, I'll just do this quickly just for the sake of completeness. But yeah, I totally have to do this. Right. Yeah, this is a major deja vu. I'm sorry. Okay. Yes. All right. So we've done this before. What now I'm okay. Now that we've done it twice, you're totally deeply responsible for this. You've got to know this like the back of your mind. You've got to have this tattooed on the inside of your eyelid. So every time you blink, you see it. Ew, that's gross. I didn't say that. But what I am honestly saying is now that we have done it twice, now that hopefully I've just run through it in the context of that big English explanation of energy, hopefully you see this is classic application of conservation of energy. That's what it is. And the real problem solving upshot of all this, and I promise I'm moving on. Just please note that the one thing we did, that all of my explanation is really to say, you can't do this problem by just saying 1/2 mv squared equals 1/2 kx squared. Really, really, all my yammering for the last 2 weeks comes down to that people in physics have a tendency to think that when they have to do an energy problem, they do something like set the kinetic equal to the potential. That's really what a lot of people do, especially when they panic on exams, is they think energy, they know something about kinetic, they know something about potential, and so they set kinetic equal to potential. A lot of times people will say things like 1/2 mv squared equals 1/2 kx squared, or 1/2 mv squared equals mgh or something. What I'm trying to say with all of this is occasionally it works out that by coincidence, that's not a wrong thing to say. Like at the end of question 4, that worked. But in general, that is not a right thing to say, and it doesn't work for question 5. In general, energy conservation does not mean kinetic equals potential. It means the sum of kinetic plus potential over here equals the sum of kinetic plus potential over there. Okay, that's my punchline. That's the upshot. That's like way too much on that. Thank you for your patience. Thank you for your citizenship. Let's go on to question 6. Or I mean, but if there are questions, please do put them in the chat. All right, we're on question 6 now. Oh my God. Okay, question 6. And question 6, which I believe is the one that I believe that it is. Question 6 is question 6 is question 6 is. Oh yeah. Okay. Oh yeah. All right. Good. Okay. To be clear with question 6, to cut to the chase, question 6 is the one that I think if people were still hanging on when they were doing the homework, by the time they got to question 6, I think most people get question 6 correct. I think many, many people know the answer to question 6 or feel they know it without doing any work. I think many people even, or just guess it, or if they're, I think this is what people guess. And I'm here to tell you your guess is right. It is exactly what you think. It just gets to 15 centimeters on the other side. But I'm also here to tell you that it's not just that you guess that, it's not just that that's the only reasonable number to assume. It's precisely a result of saying that energy is conserved, right? We're literally saying that. We're saying that there's a one-to-one correspondence between spot and speed. So this question in English sounds like, okay, how far does it get to the other side? But it's really saying, what's the other position at which, or is there any other position at which V is 0. If you do the math, like we're really asking what are the two roots of x squared when we solve for x such that V is 0. There's two roots for, I mean, there's two roots, it's a quadratic. And one of them is positive and the other one's negative. Like we are literally saying that there is a speed to spot correspondence. We're asking for the other spot at which V is 0. It is negative 0.15. And lastly, so again, I mean, you know the answer is this, or you would guess that the answer is this. There's not, but it is rigorously this. It's mathematically this. And here's the extra thing I want to say. What many of you might be thinking is, okay, yeah, it'll go to the other side, but that's like a perfect ideal spring. Like, who are we kidding? A realistic spring, like in the lab, is not literally going to go all the way to the other side, as far as it started, you might say. That may be true. I mean, I think some springs are better than others. And remember, again, my standard of science, maybe no spring is perfect, but I absolutely think there are springs for which whatever measuring equipment you're using to measure all the parameters of that spring, for which there are springs that are good enough relative to their measuring equipment, such that whatever amount they fall shy on the other side, whatever amount that they fall shy of 0.15 might be too small to be picked up on the measuring equipment appropriate to measure every other parameter of the spring. Remember again that that's the standard of science. When we say something's negligible, we mean not measurable. So first of all, I actually absolutely think there are springs that are good enough to do this. But second of all, let me be clear about another thing. You can say right now, okay, that's an ideal optimum spring, like only a realistic everyday spring won't go all the way to 0.15 on the other side. And I say that may well be true, but what you're saying is that a regular everyday crappy spring won't perfectly conserve energy. So in other words, you can say during question 6 that this answer is only true for a really well-behaved spring, but that's no more applicable to question 6 than to every other question you've already solved on the homework. And I really do mean that. Like, this whole homework is a math assignment in a way, and it didn't stop becoming a math assignment just when English words were used. So I'm just saying, if you want to qualify in the back of your mind and say, well, this answer is pending how good the spring is, yes, as is every other answer in the question. I mean, in the homework, you follow what I mean? Like once, in other words, the flip way I'm putting it is, once we're going to take energy conservation seriously as an idea, let's take it seriously. This is a consequence of it. Similarly, right. So this is as true as the math right above it is true. So similarly, we go to question 7. And again, now I'm like all babbling because I'm trying to sort of make up for inefficiency, but don't think you can't stop and ask a question. So we now go to question 7. We go to questions, and it's a very similar kind of question. I mean, if I remember it correctly, it's a very similar. Hello. It's a very similar question in that I can't read it. It's a very similar question. Yeah. Oh yeah, right. So 7 very similar questions. So how many cycles can the mass complete until it comes to permanent rest? And the answer to this, again, like the principle here, again, the principle is conservation of energy, which we established up in 4, 5, and 6. If we're believing in conservation of energy, if we're believing that all the forces doing work on this spring are conservative, i.e., if we're believing that the non-conservative force of friction is doing a negligible amount of work, then the answer that we're believing to this question is, exactly what I think you think, but also what you might think sort of skeptically about. The answer is infinity. Like, this thing will go on and on forever. Now, why am I asking these questions? I just want to, and I think that that's sort of the expected physics answer, that this thing will go on and on and on forever. But I'm here again to drum in before we go any further in the course, and especially now that we've seen each other in the lab, and that's sort of like the reality piece of all this is, I'm saying that a well-behaved spring will go on and on forever. I'm saying that a spring for which the force of friction doing work on it is negligible. And I'm saying there are such springs in the real world. I'm not saying perfect. I'm not saying springs where there's no friction. I'm saying where the friction effect is negligible. Let me be more realistic again. How do you set up such springs? Like the better behavior you want from your spring, the longer the spring has to be in comparison to any displacements to which you subject it, right? In other words, 15 centimeters is a fine amount to stretch our spring initially, as long as 15 centimeters is very, very, very small compared to the actual length of the spring. The springs we were doing in the lab were like good enough to get pretty good results on. Like a lot of you got, not these results, but different results. A lot of you got pretty good results on those springs. And that's rushing through, taking 5 data points in a sort of rushed, fun 2 hours, right? And those springs were pretty darn small, actually. Like, they're not great springs. They just came out of the box, you just played around them, and you got pretty good results, a lot of you, right? What I'm saying here is, if you want really good results, use much longer springs and subject and ask for extensions and compressions that are much smaller than the spring itself. And then again, you say, well, what do you mean much smaller, Yavram? That's kind of vague. That's not very scientific. What do you mean much smaller? And my answer is small enough that the piece of measuring equipment, the meter stick or whatever that you use to figure out the length of the original spring cannot pick up, is not precise enough to pick up the lengths of the extensions and compressions to which you subject it. Like everything, this is the difference in science and math. In science, our arbiter of truth is measurement. If something is big enough to exist, but not big enough to be quantified in comparison to other measurement, if a quantity is big enough to exist and make a difference, but not big enough to be quantified by our measuring equipment, not big enough to be compared to other small things on our measuring equipment, then the quantity is negligible. Then it's immeasurable. Then it is what we mean by take it to the limit. Like, right? And then we can say very powerful things about it. So in the lab, there is a concept of infinitely small, infinitely large, are approaching the limit as we conceive of perfection. There's all of that in the lab. And all of those limits and calculus and infinitesimal, like threshold zones that sound so vague, maybe sometimes in a math class, are literally just the zones of things that are happening, but beyond our ability to measure. Like, and that's a very important zone. Okay, so anyway, so I'm saying this thing will go on. This thing, if it's a perfect spring that's following the math of every item before it on this homework sheet, then we're going to assume from now on, if we're talking about an optimum spring, if we're talking about a true energy conserving system, from now on, whether it's a spring, a mass on a spring, or a really good pendulum, like a planar, small angle, long string pendulum, we're going to every single, in fact, I'm going to write this right now. I'm saying from now on, Okay. The real point of these questions, like questions 5, 6, and 7. Yeah, questions, questions 5, but questions 4, 5, 6, and 7. The point of these questions is we're really trying to nail down now what it means to conserve energy in an oscillating system. From now on, any oscillating system that conserves energy, any oscillating system that ultimately obeys some version of Hooke's law, we're going to from now on call a harmonic oscillator. I'm actually going to be more specific really soon about the rigorous definition of harmonic. But right now I'm saying any steady energy conserving oscillator, we're going to call a harmonic oscillator from now on. That certainly includes masses on springs. That also includes simple, planar, small angle pendulums. Okay, they are both, and so please be writing this down maybe somehow. I'm saying masses on springs and simple, small angle pendulums are two of many examples of what we're going to call a harmonic oscillator. Ultimately, a harmonic oscillator is any system that behaves like an ideal mass on a spring. Like the ideal mass on the spring is the central, most vivid example of all harmonic oscillators in the world. I mean, that's why we're spending so much time on it. We're going to assume from now on that harmonic oscillators undergo a type of motion that is cyclical and patterned and regular and predictable in all of the ways that we've been saying questions 1 through 7 so far. Like all of those simple symmetric intuitions that you might have, like it's going to go back and forth forever. It's going to go to the other side the same way it went to the first side. And if you're intuitively guessing like, okay, so I guess whenever, when it's at 0.15 meters on the right, it has 0 speed. When it's at negative 0.15 meters, like on the left, it has 0 speed. So then if you're also guessing, oh, I guess it's always going to work out like that. If it's at 0.095 meters on the right side, it'll have a velocity of +3. And if it's at negative 0.095 on the other side, it'll have a velocity of -3. Like any symmetric, patterned, intuitive guesses that you might make like that are right about a system like this. A system like this is highly patterned, highly predictable, and nice in those ways. It gives us huge amounts of predictive power. It also then raises interesting questions that we're going to get to in question 9. But from now on, these kind of energy conserving systems are reliable in all the ways that we're thinking. They're called harmonic oscillators. And again, they are realistic and possible to various extents in a lab. Like again, if nothing else, if you got vaguely okay results the last 2 weeks, you're showing that even with a clunky little, not that great piece of metal that's been sitting in a COVID box for 2 years, with under the guise of a bunch of students who don't have to hand in anything in and are kind of like not under the gun, and not like, we casually did 2 labs and we casually got pretty good results. That tells you that if we were actually NASA, or if we were actually or if like we were actually like government funded, gun to our heads, and highly equipped laboratory trying to study like the motion of spring, I think we could make springs that were pretty darn precise and pretty much did come super close to going back and forth like forever without ceasing. Like literally forever? No, but long enough that our clocks would run out before they would. By the way, what do you think we make clocks out of? Masses on springs and pendulums. But anyway, right? So from now on, and final point on all this, what we're really interested in the long term in this class and in life, not to give away anything, but like what we really ultimately care about are harmonic oscillators that already exist in nature. What we ultimately care about in physics, and certainly in like PChem, are atomic oscillators. And believe me, they exist. I mean, they certainly exist. And you can imagine like an atomic oscillator, if it behaves basically according to the math that we're talking about here, well, an atomic oscillator is not subject to experimental error or a heck of a lot of friction. So So believe me, there are reliable systems like this in the world. That's what we're studying from here on in. And we should assume all the reliabilities that these answers tend to imply so far. Okay, so I'm babbling. I'm like feeling like I'm talking about these oscillators like they're my own children, but they kind of are. Okay, wait, no, sorry. Oh, okay, I'm looking at the chat. Okay. I'm just responding to something in the chat, and then I'm going to go on. But anybody can put questions. I mean, I know I'm babbling, so please feel free to ask questions. Hold on, there's something in there. No, there are some good questions in the direct chat. Really, there was more than one good question in the direct chat, which I just tried to respond to. Again, I just want to say I'm very tempted to, not to mention names, but I'm tempted to deal with the questions like publicly with everybody. I'm going to make the decision not to, because I think some people are itching for me to sort of move on for the moment. But I want to say, so I'm fighting an internal battle. I want to say that the larger question, like that I'm getting all hung up on, and that is being, we could have a whole really good class discussion about certain things that are in the direct chat right now. And again, there's more than one of them. But the larger issue, and I've struggled with this for years, believe me, so I'm tempted, but just the larger plea I want to make for the moment to everybody, especially because like physics is supposed to be where we use high level abstract math to describe the actual world, the real world of space and time. It's a beautiful thing that we're trying to do in physics. It's also a very fine line and a delicate line that we're trying to walk in physics. The one thing I just want to put out there for your consideration, and again, like I've churned over this many times in my mind, it's easier said than done, but whenever we talk, just remember that when we talk about such things as limits or infinitesimals or derivatives or negligible amounts of friction or perfection or negligible amounts of deviation from perfection, like that can be to many people, all those zones can sound to people, to all of us, as so abstract as to not have to do with the real world. There could be this ongoing struggle of like, wait, right now, are you just talking in your head, Yaverbaum? Or are you actually talking about something that could be done in a lab or in technology or like in the actual world? Like, are we just doing abstract math now, or are we doing something closer to engineering? Oh, cool, awesome, thank you. And it's a very fair question, especially those of you are going on to different jobs in life. Some of you are going to be very, very academic, maybe, or want to be. Some of you like totally want to work for the government or like the police. Like that's right. That's like two ends of the spectrum. What I'm here to tell you, what I've really found myself is that what's beautiful, science is not the same thing as math, and science is not the same thing as technology either. Science is science. What's beautiful about it to me is that it's all arbitrated in the end by measurement. And that means there actually is a clear threshold for what we can quantify and what we can't. And it doesn't mean that we can't talk about the things that we can't quantify. It just means that we can distinguish the things that we can't quantify from the things that we can quantify. It means we can like openly talk about, oh, this, when we say something's infinitely small, like for me, that used to be just a very crazy mathematical abstraction that basically seemed like a lie to me, like infinitely small, like it's so close, it's like as close as I want to zero, but it's not zero. Like that sounds like just BS to me. And it especially sounds BS to me, to the part of me that wants to do like either math that seems math is supposed to be really clear cut in black and white. I feel like sometimes, and science is supposed to be really real world. And I feel like when someone says it's as close as you want it to be to zero, but it's not actually zero, I can feel like you're not talking math or science when you say that. You're just talking some crazy stuff in your mind. What I'm here to say is no. When someone says as close to zero as it can conceivably be without actually being zero, what they literally mean is it's a number that exists, but it's too small for me to measure. That's like a very meaningful thing to say. Like, do whatever you want with it, but just know it's a concrete thing to say. It's a number that like if I put something on on my digital balance, I take an object, put it on the digital balance, but it's so light that the digital balance doesn't register, like the needle doesn't move at all. Well, I saw myself put something there. So there is a mass there. It's a mass, but it's a mass that is below the threshold of measurement. That's different from a mass of 1.2. And it's also different from putting nothing on the digital balance, right? It's like something, but it's immeasurably small. Do whatever you want with that, but just know like that's a category that we can say and do something. And so I would call that, I would say that's an example where it's in the limit as the mass approaches zero. And and why? Because I could put another thing on the digital balance. I could put another thing that is a different object that I don't have any reason to believe has the exact same mass as the first one. Like first I put like a P, and then I put like, I don't know, then I put like a piece of lint on the digital balance. They're two totally different objects. I have an intuition that it would be really crazily low probability that they both have the exact same mass. And I might even have an intuition looking at the P and looking at the lint that I even think the lint might have a smaller mass. But I put them both on the digital balance and they both register zero. So what does that mean? They're different, they exist, but they're not quantifiably or measurably different. So I have to deal with it. So I would say that's an example of what it means to say as close to zero as possible without being zero. That's in the limit. It's like, that's what we mean by infinitesimal. Now, what do you do with that is like your choice, but it is a thing. Like it allows me to picture what I mean when I say limits and stuff like that. Okay, I'm totally bad, but it's why science is cool, and it's not just math, and it's not just technology. It's like a way of thinking and interacting with the real world. But okay, I'm looking at the chat again. Sorry. Oh, no problem. Cool. Oh, totally. I mean, the answer to that. So we are as limited, but our power as scientists, our access to the truth is both 100%. Sorry, I shouldn't say 100%. Our access to the truth, our claim to the truth as scientists is both supported by and limited by instrumentation. It is all about our instrumentation. That is why we trust ourselves. And that sounds so dumb. And I'm responding to something in the private chat now. That may again sound so, like when I first heard that, I was like, really? Like, really? Like you're gonna rave to me about like black holes and like twin paradox and like big bangs and all these great cosmic physics, cool weirdness. And then you're going to tell me in the end that the reason I should believe any physics is because of like a meter stick. Like it all comes down to, or like our like freaking calipers and our like whatever, like our stupid little protractors and instruments in the lab. Like that's the depth and the profundity of physics. The answer is yes, it totally is, because the meter sticks or the calipers or the telescope or like whatever instrument we use to measure, the reason that we put all of our faith or whatever and all of our stock and trade on that is because that telescope or that meter stick or whatever it is the thing which, when once accompanied by a good instruction manual or a good lab procedure, can be sent to anybody in the country, anybody on planet Earth, anybody of a future generation, anybody, I guess, of a past generation, anybody on the moon, it can be sent to anybody else, and it can say, here, you use this instrument and you test and you see what you get. Don't trust me. Don't trust my crazy mind. Don't trust my internal narcissistic mind. What I'm saying is, I didn't just live in my mind. I tried to check with the world, and I tried to check with reality with an instrument that I'm giving over to you with instructions of what I did. So you, and when I say you, I mean anybody, but I also mean everybody of the world. I'm saying my instrument is where I put down my own ego or my own crazy internal world. And I say, this is my interface to external reality. Now you use it and you see what you get. And if we all use it and we all got 3 millimeters or whatever, then now we have as close as we're going to get to truth as I can understand as a scientist. Like, I'm not, in other words, the reason we trust the instruments is so that we're all recognizing we don't trust ourselves. And that's why the world should trust scientists, because scientists are saying, don't trust us. We're smart enough to know not to trust ourselves. We're saying, trust you. Here's the equipment. Like, you see what I'm like? That is what makes science science. What makes science science is a method of recognizing our limitations and turning over the discussion to something outside of us. That's what we're trying to do. I mean, obviously we fail a lot, and obviously people cheat, but like so it does totally come down to instruments. Instruments are our credibility, but yes, they are also our limitation. But we have credibility because we admit our limitations, unlike certain other fields of study where there's just like, no, anyway, I'm going to stop now. Clearly I have no limitations. So, okay. But yeah, it's all about instrumentations. That's also why your like most real course in this major is called instrumental, probably. But okay, I'm totally moving on now. I didn't say that. Well, go. Okay, all right, so I'm moving on. Okay, babble, babble, babble. All right, so now question 8. Oh, question 8 now gets sort of interesting in a different way. Sorry. Ooh. But yeah, see, put all my energy into not raving about how much I love all you guys in the lab, and then I end up like raving about how much I love instruments. But okay, question 8. So question 8 is, oh yes, okay. Oh, okay. Okay. Okay, so I'm doing now. I'm finally on question 8. I'm on question 8. Okay. We're gonna try to this too, if I'm not careful, could be a whole big discussion. Let me try to make it not that way. Totally well. Anybody can put any answers to this they want in the chat. If you think you have answers to this, please feel free to put in the chat. That's another thing I owe you is more. I have to open up more class participation portals, like for showing video and stuff like that. I'm saying that to remind myself I've got to do that. But feel free to put answers in the chat if you want to this. But I'm just going to start saying answers to keep us moving along. Like, so we're looking at, remember, this is question 8, and just to, maybe you're looking at the sheet, but just to remind you, we're just now investigating that first segment of motion where the mass starts at the initial position and starts moving in of its own accord from x naught to the equilibrium position of 0. Now remember, and we're going to ask a bunch of questions like what happens to its velocity, what happens to its acceleration, then we're going to ask about its jerk. remember, this is a little confusing because we're only asking about magnitudes here. In other words, we're asking about the magnitude of velocity, which is otherwise known as speed. Then we're going to ask about the magnitude of acceleration, but there's no special word for that. And we're only asking whether the quantity, the measurement, increases, decreases, or stays the same. So I guess I'm going to sort of cut to the chase here, but stop me if you disagree or anything like that. From the initial position to the equilibrium position, well, it starts at speed 0. The whole problem starts from rest, and then the thing is pulled in by the spring. It's building up speed as it goes. We know by the time it gets to the equilibrium position, it achieves a maximum speed of 3.87 meters per second. We also even know that at some point in the middle, like as it reaches 0.095 meters from the equilibrium position, it's gotten up to a speed of 3. So we've got like a lot of data points here. We know it's going from 0 meters per second, continuously to 3 meters per second, continuously to 3.87 meters per second. So for sure, I mean, it's not meant to be a trick. We're just trying to build a pattern here. For sure, I think the speed is going up. To be clear too, I actually think the velocities are negative numbers, to be clear or to be thorough, like, right? I mean, the thing is moving to the left, and we've established in our coordinate system that everything to the right is positive and everything to the left is negative. So technically speaking, that original velocity is 0, and then the next velocity is like really actually -3, and then the next velocity is really -3.87. I mean, for whatever, if you're tracking this, but the question is just asking about magnitude. So the answer is the magnitude of the velocity is increasing in that first segment of motion. So the object is accelerating. It is changing its velocity in a certain direction. Now, then it asks what's happening to its acceleration. Well, it definitely is accelerating. It certainly is accelerating. It's changing its velocity. But let's notice now, look at our data points, that we got from the problem, not from the lab. Its original acceleration was this enormous number, I believe, I believe it was 100 meters per second squared. Now, I also believe actually that it was negative. I believe it was pointing to the left. I think the thing is being forced, being pulled to the left. I think it's accelerating to the left with a negative number of what I think we said was -100. Or no, maybe it was, I think it was 100. It was 30. Yeah, it was 100 meters per second squared negative. Okay, it was negative. But now we're only asking about magnitude. So let's not get confused or hung up on the fact that it was negative. The magnitude of acceleration at the beginning was this enormous number of 100 because it's being pulled very hard because the spring is being extended very intensely. So now the thing starts coming in, and we know it's accelerating, it's speeding up. We just established that. But the acceleration value seems to be heading toward a value of 0, right? We said that when this object gets to the equilibrium position, it will have an acceleration of 0. It started with a magnitude of 100, again, granted -100, but I don't care. It started with an enormous amount of acceleration, 100 units, meters per second squared, and a lot of force. Then as it gets closer and closer, the force magnitude gets lesser and lesser because F equals -kx, and the x is getting smaller and smaller until it gets to the equilibrium position where the x is 0 and the force and therefore the acceleration are both 0. So it seems to me that while this while the magnitude of acceleration is increasing that entire time continuously, the acceleration is decreasing. Now let's just pause on that. I think the numbers are not that hard. I think I should never say I might be doing the wrong one. Oh, fair enough. Yeah, actually, sorry, direct chat person. Yeah. Yeah, okay. So someone's asking, someone in the direct chat is raising, it's true that this has happened for some reason. Many people, and I don't know, I did something in the question where it leads to misinterpretations for not only just one person. I only mean to be asking here what's happening in the first segment of the motion. There are people every semester that sort of give me a whole breakdown of all the different answers that happen, like at every different segment, which would be a great question. Like, I'm all happy for that. Like, in other words, a lot of people are asking or answering something even more thorough and even more involved than what I'm asking. And kudos to them. They're giving even more, and they're thinking it through properly. But right now, all I'm asking for anybody who's, and if you did that in your homework, don't worry about it. Like, you didn't do anything wrong. You just did more. I mean, you're still getting full credit. Don't worry about it. But to everybody, I'm just trying to, on purpose, like hone in on just this first segment. And the reason I'm honing in on it is because if we take a look at just this first segment, I don't think the numbers are hard. Like, I don't think this is complicated, but I do think it's sort of surprising. And if you don't just play with raw numbers and you step back and look at English, for some of us in the room, it may be a surprising thing to notice that something can be increasing in speed while decreasing in acceleration. Now, that is totally possible in physics, and it does happen all the time. And acceleration is different from velocity. One is the derivative of the other, but they are different and they can be independent. But, I'm just looking at chat. Yeah. Oh, this is a good question too. Okay. Sorry. Right. So, okay. There's another good question in the direct chat. Let me I just want to point out to everybody, please take a moment in your own private Idaho, like honestly to yourselves, notice I'm saying this thing is gaining speed. It is accelerating while it's losing acceleration. Just ask yourself, each one of you, if you really are fully comfortable with that. Like, because you may not have ever noticed before that was possible. You might just be I don't want you to just accept it as just like random words. Like, we are saying something that is possible in physics, but does confuse people sometimes. And in fact, it's an interesting feature, particularly of an oscillator, that this can happen. So I'm just saying, so if anybody does have an issue with that, at the very least, put in the private chat, like, wait, what? Like, or whatever. Because for some people, this is the first time they ever encounter this consciously, and it's okay to do that. But then, so take a moment with that. But then someone also in the private chat just asked another very fair question. Right, totally fair. With questions like this that are more directly Englishy or directly like observational, I agree. It's a little bit hard to do the whole 5-step method here. I think you could still do a better job of it than I'm doing right now. I'm starting to drift into just giving you answers or talk because I'm sort of getting concerned about time. And I am more and more as we go over these homeworks. I'm not necessarily going to break down the whole 5-step method all the time. Now that I feel like I've showed it to you, I'm sometimes just going to be saying what I want to say. I think that, so my answer is, I think when you do your homework, you could come closer to respecting the 5-step method with a question like this than I have right here. All I've done here is like drawn arrows. You could come closer to respecting the method, but I agree with like a straight observational question like this, you can't fully do the 5-step method. And I do agree, and I totally respect that. And you wouldn't lose a lot of points or whatever if you didn't. But try to say more than what I'm just saying here. Like really, like, I'm talking a lot and I'm not writing things down as much because I'm running out of time. But like, I literally did say things like, well, at x equals 0.15, v equals 0. At x equals 0, v equaled 3.87. Like but I just failed to write that down here. So there is more that could be written down. But okay, but yes, I hear your point. Now, because I am aware that there's 4 minutes, the hard question and the interesting question of this, and sadly, I guess where we're going to end for this week, and then it's all about question 9 for the rest of like our lives. The sort of interesting question is this last one where it asks about the jerk. Well, the jerk is at the front of the room, like wearing a gray jacket, but the jerk is a word that maybe some of you might never have heard before. Jerk means, it is a word. I mean, in physics, it doesn't come up a lot, but it means that. It means right? It means the rate of change, the instantaneous rate of change of acceleration, which is to say the rate of change of the rate of change of the rate of change of position with respect to time. That's what jerk means. That's what I'm asking about now. Now, I'm not assuming that you would just intuitively know anything about the jerk, but I'm actually kind of asking if we could see any kind of pattern emerging and infer anything from the pattern. In fact, that's actually all I can really ask is, can we see anything emerging in this pattern? Well, our pattern, and I know we have 2 minutes, our pattern isn't that huge. We only have sort of 2 data points in this pattern. We see that the velocity is going up, the acceleration is going down. But if we notice that these are all derivatives of a function, maybe in order to help us, this is my last page, I'll try to do this quickly. Okay, I have like 1 minute, so I'm going to say very quickly. Look, on this page, we looked at the derivative of position with respect to time, velocity, it was going up. Then we looked at the derivative of that, acceleration, it was going down. Then we're getting asked to go one step further. In order to do that, why don't we go one step back? Let's just look at the position. Oops, sorry. Let's look at the position itself for a moment. What's the position values doing from x equals 0.15 to 0? And I'm just talking about magnitudes, not a trick question. The position values from 0.15 to 0 are going down. That's not an arrow, that's an arrow. The position values are going down. So just based on pattern alone, and I know I have like 30 seconds, notice the position's going down, then back a page. The derivative is going up, then the derivative of that is going down. That's 3 points right there. That's not a lot, but that's a pattern. If I had to guess right now, just based on pattern, I would guess that the jerk is going up. I would guess that it's not remaining constant. I would guess that it's not going down. I guess that it's going up. And since we have to end right now, I'm going to tell you that guess is right. And this pattern does go on forever. The derivatives go on forever. This function, f equals negative kx, is infinitely differentiable. That's freaking interesting. Like, in other words, all the patterns that you think about, it goes to the right, then it goes to the left, it goes fast, then it goes slow. The acceleration goes up, then it goes down. Not only are all of those infinite cycles, but there's an infinitude of those cycles. Every rate of change that you could conceive of on this thing is cycling back and forth in response to the derivative below it, going back. So just like positions are going back and forth, getting smoothly slower, lower and smoothly higher. Velocities are going back and forth, getting smoothly lower and smoothly higher. Accelerations are going, this goes on forever. It's actually a fascinating motion. It's a package of infinite derivatives all cycling. So there's more for us to unpack, and that's all contained in question 9. That's where we'll pick up on Monday. I owe you stuff. You've been very kind. I hope to see you physically again, but until then, I will see you electronically on Monday. So goodbye. So thank you all very much. Have a great weekend. Yes, have a great weekend. Thank you, guys. Thank you. I'm turning off. Thank you guys so much.